recent breakthroughs in the understanding of topological states in quantum mechanics.
Thank you very much. I'm very grateful for the invitation to come here to speak to you about some recent developments in quantum metaphysics. Generally goes under the name of quantum spin Hall effect, topological insulators, and topological superconductors. So let me first acknowledge my collaborators, my group at Stanford, and since then people have gone to different places. Shoucheng Zhang is the new faculty member at Stanford. Andrew Bernowitz, who worked a lot with us, and now a faculty member at Princeton, and Hongping Wu at UCSD. Extensive collaboration with the Stanford experimentalists. This is also a true international collaboration with colleagues at Würzburg, Germany, and also with my distinguished colleagues at IOP, who are now very well represented here at ICAM and also at Tsinghua University. So we're talking about the subject of quantum matter. And in the case of when you look at the history, it has always been that the search of new elements defined the golden age of chemistry. Search for new particles defined the golden age of particle physics. But in this discipline of quantum metaphysics, what is kind of the fundamental pursuit? The fundamental pursuit is to search for new states of matter. And we know that the same basic ingredients, for example, H2O molecule, can form different phases when we go into the quantum world of the electron. The very same electron can form many different states of matter, the crystal, solid, the magnet, and superconductor. So after quantum metaphysicists discovered all these phases or states of matter, they also formulated a principle which classified all of them, most of them, and that's called the principle of broken symmetry. We say crystal is different because it breaks translational symmetry, the magnet is different because it breaks rotational symmetry, and superconductor is different because it breaks the gauge symmetry. And that gives you the concept of order parameters, the effective field theory in terms of order parameters, and so on and so forth. And that pretty much has been the paradigm in the last 50 or 60 years, ever since Landau formulated these concepts. But in 1980, a new state of matter was discovered, and that's the quantum Hall effect. Now, it is different from any ordinary states of matter, not in the sense of some conventional order parameter that breaks some symmetry, but in the sense that it's topologically different. If you take the two-dimensional system of the quantum two-dimensional system of semiconductors in large magnetic fields, the Hall effect goes in a quantized fashion, and the whole conductance is always an integer times a fundamental quantum of conductance E squared over H. And it has been realized by Fowler and co-worker that this integer n, which is so precisely quantized to a precision to better than 1 part in 10 million, is actually a topological number. And it is, if you do some violence to the system in making making distortions in many different ways, adding disorder, changing thickness, and so on and so forth, you are not going to change this topological integer. And that's why these plateaus are so well quantized. So in a very precise sense, we classify topological states of matter by such topological invariant. And it is zero in ordinary state, but it's non-zero in a topologically non-trivial state. Maybe even more fundamental characterization of these topological states is that they are all described by topological field theories. So these are like the counterpart of field theories based on order parameter in the broken symmetry states I discussed earlier. But for those topological states, they're described by some topological field theory. And in the case of quantum Hall effect, it has been worked out by us that this is Chen-Simons field theory. And the coefficient, again, whether zero or non-zero, characterizes whether this is a new state, whether this is a topological state or not. So quantum metaphysics has been a very interesting but somewhat funny state. When you look at 99.999% of the states are all these broken symmetry states, and there's only one and single example, which is the quantum Hall effect, which is a topologically non-trivial state. So how can that be? So we have always been dreaming about and searching for new topological states in quantum metaphysics.
Can I ask a question?
Yeah.
When you say topology, you mean what's the space in which I think of this.
Yeah. This is the best way to think about topology is that you think about field theories. For example, ordinary matter are described by some Maxwell equations. Okay? So now this quantum Hall effect is described by a set of equations which are called Shoucheng field equations. In what way are they different? Well, yeah, so you asked a very, very good question. So if I write down such a field theory, first in glass space, it takes such a form. And you notice the use of the epsilon test. Okay? So now if I try to write such a field theory in curved space, it takes exactly the same form. And that will not be true, for example, Maxwell equation. When you write in curved space, it depends on the metric. So these things only depend on the topology of the space, not on the metric of the space. And so that thing will come over and over again, the whole concept of topological field theory. Very good question. But in recent years, there has been a breakthrough. A new state has been discovered. Generally goes under the name of topological insulator. And it's also predicted theoretically before it was experimentally observed. So in 2006, we predicted that a mercury telluride quantum well will display is an example of the two-dimensional topological insulator, or the quantum spin Hall effect. And less than 1 year after our prediction, it was experimentally observed at University of Würzburg by Lawrence Wallenkamp's position. Since then, progress has been very fast. Three-dimensional topological insulator, Fu and Kane, and the theory and the beautiful experiment by Princeton group led by Sahid Kasam. And also the theoretical work we did, collaboration between Stanford University and IOP, and the beautiful experimental work done at Princeton and at Stanford. So this is the story I like to tell you, and has now been broadly recognized that this topological insulator is a new state of quantum matter. It's fundamentally different from any other ordinary broken symmetry state as we know, and it's also fundamentally different from the quantum Hall effect in the sense it does not break time reversal symmetry. And it has been recognized by science as one of the key breakthroughs among all sciences in 2007. So, even though these concepts of topology sounds very fancy, I would like to tell you that there are only two equations you need to remember. One is 2 equals to 1 plus 1, and the other is 4 equals to 2 plus 2. Okay? So what do I mean by that? So let's make life very, very simple. We go to one dimension and forget about the spin degree of the electron. So then you have a one-dimensional spinless fermion, but you will have two low energy degree of freedom. You will have a forward mover if you linearize here, and you will have a backward mover if you linearize here. And that's the common sense that if we live in one dimension, we can either move forward or we can move backward. So in the simplest case, you would always have 2 degrees of freedom in one dimension. What the quantum Hall effect does is to say that 2 equals to 1 plus 1, that you're spatially separating this one-dimensional channel in upper channel where you're only moving forward, and in a lower channel where you're only moving backwards. Okay? So the advantage of doing that is that if you live in one-dimensional world, if you are moving forward, you hit something, you will be bounced back. So the idea of quantum Hall effect is like very much the way we build our highway system. You move the counter-propagating traffic spatially separated fashion. Okay? So then in this case, nothing conducts inside, but on the edge it can conduct. But because the counter-moving traffic are spatially separated, if you hit something, there's very, very low probability that it will move back, because in order to move back, you have to jump all the way across the sample, and then only then you can move back. And that probability is exponentially suppressed. So therefore, if you hit some impurity, you simply go around and keep on moving forward. So this is an example of a dissipatingless transport in condensate. The only other example we know is superconductivity. So on this one-dimensional channel, nothing can move back. And that's one of the reasons why the plateau is so well compressed. So we do physics by generalizing. And if somebody already wrote down the equation 2 equals to 1 plus 1, what do we do next? We write 4 equals to 2 plus 2. And that's because in a one-dimensional system, this is a tremendous simplification. In fact, you also have the spinning degree of freedom of the electron. So you have spin up, spin down, forward moving, and backward moving. So altogether, you have 4 degrees of freedom rather than 2. So then you can write 4 equals to 2 plus 2, so that you put 2 channels upstairs and 2 channels downstairs. Now this looks a little bit like a trivial generalization of the idea of quantum Hall, but there's a new idea. That there are several ways of writing 4 equals to 2 plus 2, but there's only one unique way to write 4 equals to 2 plus 2 in a way that's time reversal invariant. Because when you look at this situation, time reversal symmetry is broken. If you live on the upper edge, you see only things moving forward, nothing moves back. Time reversal symmetry is broken, and that's why it requires a high magnetic field to realize such a situation. But if you write 4 equals to 2 plus 2, you're in a situation that you have up spin moving forward and down spin moving backward. If you reverse the arrow of time, forward mover becomes backward mover, spin up becomes spin down, and that is a time reversal invariant decomposition. So therefore, such a situation can be realized in principle without magnetic field. This is great news, right? Quantum Hall effect we all know and love, but it's not very practical. How can you build an electronic system in a fantastic magnetic field? But such a situation can be realized without any external magnetic field. So this kind of idea was proposed independently by King and Lee without Landau levels, and by Bernadette and myself with Landau levels, but always without time reversal symmetry breaking. But now you may say, wait a minute, what good does this do for you? Here you made the argument that only things moving forward, so therefore if you hit something, there's no way for it to move back. But here you have still 2 counterpropagating channels, both the forward mover and the backward mover. What if you hit something? It turns out that it cannot go back, and the reason it cannot is due to the deeply profound and yet mysterious principle of quantum mechanics. In quantum mechanics, we learned that if you have an integer spin particle and you rotate by 2 pi, the wave function goes back to itself. But if you have an half integer particle and you rotate by 2 pi, the wave function goes to minus itself. And that is, to me, one of the most mysterious principles of quantum mechanics. But it turns out it's exactly this fact that leads to the protection of the quantum spin particle. And it also leads to the fact that the time reversal symmetry in quantum mechanics is very strange. That if you operate it twice, usually if we reverse the arrow of time once, past becomes present. If you reverse the arrow of time again, present becomes past. Everything should look back the same. But it's not. In quantum mechanics, when you operate it twice, it gives you -1 rather than +1. And that's deeply related to this minus sign. So now let's try to understand why this is the case, why this mysterious principle of quantum mechanics will give you the protection of edge states. Let me draw another example from daily life. For example, if you take a fancy sunglass or a nice optical instrument such as a nice camera lens, they usually come with something called anti-reflecting coating. What are they? This is a very thin dielectrical film so that you want to avoid reflection off of the camera lens or off of your sunglasses. So now when the light comes in, it has 2 possibilities. It can be reflected on the first surface, or it can reflect it on the second surface. Now if you choose the thickness of the film correctly, you can arrange such that these 2 always interfere with each other this time. The same idea we apply here. So when we look at the edge state of the quantum spin Hall effect, you see there are 2 counterpropagating channels. But that's a perfect correlation, because only upspin is moving forward and downspin is moving backwards. Now, what if you have some impurity, and let's assume these impurities are non-magnetic impurities. Now, non-magnetic impurity, in principle, can still backscatter by the effect of spin-orbit coupling, but they do not break time reversal symmetry. So therefore, if the electron is heavily moving forward and it hits an impurity, in principle, it can move back and turn around. But because of this perfect spin-orbit coupling, when it moves back, the spin has to rotate as well, from up to down. And in the process, it rotates by pi, okay, 180 degrees. But now, if the system is time reversal invariant, for every clockwise rotation, there's always the possibility of a counterclockwise rotation, which will have exactly the same probability. It turns out the probability amplitude will be the opposite. So now if it goes around and it rotates counterclockwise, the spin will follow and rotate counterclockwise as well. So when you look at the difference between these two paths of possible backscattering, in principle, their probability has to be identical because of the time reversal symmetry. But when we look at the phase difference between these two processes, you see that in one case the electron spin rotates by pi, in the other case it rotates by minus pi. The difference is pi minus pi, which is equals to 2 pi. We just reminded ourselves that in quantum mechanics, rotating spin by 2 pi, half integer spin by 2 pi, give you a minus 1. That's why these two possible backscattering paths always interfere with each other this time. So there's a perfect protection as long as there's time reversal symmetry. And like the case here, it only works roughly because you need to choose the film thickness very precisely, and you cannot always do. And even if you choose it precisely, you can only do it for one wavelength, not for all wavelengths. But this one works always because it's a fundamental principle of quantum mechanics. In the previous talk, the beautiful talk by Ali, he showed you that such a thing can be tested experimentally in STM experiments. I will go back to it a little bit later. And also, it has been directly checked in the transport experiment done by Lawrence Mollenkopf's group in Mercury telluride quantum webs. So another way to say pretty much the same thing is to look at not in real space, which we try to explain in an intuitive way, but also in energy space. So we're familiar with the concept of a semiconductor or insulator, which has a conduction band and a valence band. Now, we have known before that an insulator or semiconductor can have surface states. For example, if you arrange some particular cut of the silicon surface, it will have some surface states. So these surface states live inside the bulk band gap, and they're exponentially localized on the surface. But it turns out these surface states, so this picture naively looks very different from here. But it turns out that whenever you have such crossing or degeneracy in quantum mechanics, you should always ask whether this is kind of a protected degeneracy or some accidental degeneracy. And most surface states we have in solid state physics are not protected. That in the sense that if I miscut the surface slightly differently, this degeneracy will be removed. If they're removed, I can do even more perturbation to it and it will be removed further. So in this case, then I would say there's no qualitative difference between this group of state and that group of state, because I can call everything here conduction state and everything here valence state. There's no qualitative difference between ordinary surface state and trivial insulator. But this is not the case for the edge state of quantum spin Hall effect. Similarly, we have a conduction band and a valence band. But now you have one pair of edge states on each edge. The two edges are very far separated. We don't need to consider any coupling between them. But then you have an upspin branch moving forward and downspin branch moving backward, and they cross. And they cross at a time reversal invariant point. So at a crossing point, they exactly satisfy the Kramer's theorem. Kramer's theorem tells you that in a time reversal invariant system, you have to have a double degeneracy. And such a crossing exactly satisfies it. So if you introduce a non-magnetic disorder, you don't break time reversal symmetry, but you can do all possible other violence to it. The only thing you can do is to shift that crossing point up or down. You can never open up avoided level crossing or open up a gap so that these groups that can map onto that group. So in that sense, there's a topological difference between a quantum spin Hall state with edge state and a trivial insulator without edge state, because these edge states crossing are protected. And in that sense, there's a topological difference. Now, some of you will not be completely satisfied by an argument like this because it uses single particle band picture, and I will give you the most general argument, which does not depend on the band picture later.
So, Shoucheng,
yeah.
Can I say then that the space is a space of quantum numbers?
The space of quantum, yeah. So, well, basically, yeah. So let me be a little more precise. So we draw these pictures when we explain the mathematical concept of topology. We say there's an ordinary band, and then there's a Mobius strip. And they're different in the sense that here that end goes around, go back to itself, and here it doesn't. But, of course, if you take a scissor, you can cut it here, and you can remove it. So there's some violent operation you can do, mapping from here to here. But as long as you do smooth distortion, you can now go from one to the other. How do we translate this concept into connected physics? In connected physics, if you have a state that has a gap, So then basically that's in the space of Hamiltonians. Within the space of Hamiltonian, I allow you to do all possible distortions, but you cannot do the violent thing of collapsing the gap. So the space is the space of Hamiltonians, and you're doing all possible variations to it, but with the condition that you're not allowed to collapse the gamut or collapse the bulk gap. So the analog of collapsing the bulk gap is like taking a scissor and cutting it. So that's not allowed. But as long as you remain in the adiabatic, and this is actually the sense of adiabaticity defined by Landau. So if you always maintain the gap, so then I can always change the Hamiltonian at a rate that's lower than h bar divided by the gap. So then I can define within the space of all Hamiltonians whether I can map some state to some others, and the claim is that you cannot without collapsing the gap. So these are the beautiful concepts of topology, and directly hints that there is such a new state. But now we're faced with the nasty job of translating topology into quantum chemistry, because we have to somehow find this state in nature. And for a while, it was quite frustrating. There was some of the early proposals didn't work out. But one day, when I was talking to a semiconductor physicist, he showed me this beautiful chart of like a periodic table for semiconductors. Everything you know about semiconductors in this chart, and it's plotted in the space of energy, gap, and that is constant. And it's a very, very useful chart, because if you want to make a red laser, you immediately know which semiconductor to pick. If you want to make a heterojunction, make some sandwich, you have to stack them vertically, because they all have the same lattice constant. But when I looked at this diagram, suddenly there's something very strange that occurred to me. That this diagram has an absolute zero. The energy of almost all the semiconductors, energy gap, is positive. But there's only one semiconductor, which is outlier, called mercury telluride, which has a negative gap. And it's exactly this negative gap which turns out to be the key crucial ingredient needed for the quantum spin problem. It turns out that it was my education as a field theorist that I know something like the sign of the Dirac mass directly determines the coefficient of the topological term. So this abstract thinking about topological field theory in this particular instance directly led to the discovery of the actual state in quantum chemistry. What do I exactly mean by a negative gap? So semiconductor band structure is very easy to understand. If you have S level and a P level, the conduction band is formed by the merging of the S level, and the valence band is obtained by merging the P level in a solid. But we know that there is something called spin-orbit coupling. So if you have the P level and the spin-orbit coupling, it will split into P3 half and P1 half. And and when you group them into a band, this is the band structure of ordinary semiconductors, such as gallium arsenide that Ali talked about, or cadmium telluride. But we know that in the periodic table, that as you go down lower and lower, the spin-orbit coupling increases quadratically. So by the time you get into mercury, a very funny thing has happened, that the spin-orbit splitting of the P level overwhelmed original level difference between S and P. So therefore, in that sense, some band inversion has happened, that the P level lies above the S level, and that gap, if you define the sign to be S minus P, will become negative. And that's the reason why mercury telluride has a negative gap. So now you can put mercury telluride as a sandwich structure between mercury telluride and cadmium telluride, and then you know for sure that as you increase the thickness of mercury telluride layer, somewhere in between, a quantum phase transition has to happen where this S level and the P level will cross each other. And that you can predict very well theoretically. It happens about 6 nanometers in thickness of mercury telluride layer. So the reason this band inversion is important is because it's the key mechanism towards topologically insulating behavior. So if you write down a simple tight binding model for 4x4, 4 levels, the P levels and the S levels, most strongest spin-orbit coupled P level, and then it groups into, it's a 4x4 matrix, and then it becomes block diagonal in the 2x2 space. So this is in the space of S level and the P level for spin up. And because S and P have the opposite parity, the matrix element has to be odd in parity. So it's linear in K. And on the diagonal element, it tells you the level difference between S and P. And as we remember, that changes sign as we change the thickness. So it turns out that in the continuum limit, this is exactly a Dirac equation in 2 + 1 dimension. But the mass of the Dirac equation will change sign as you change the thickness. So now what happens once it becomes negative? So once it becomes negative, but outside is the vacuum, or you can think of outside as being some topologically trivial material, such as chemotherapy, which has a positive mass. So then the sample boundary looks like the domain wall of the Dirac mass. Okay? And anyone can solve a one-dimensional Dirac equation, and you will immediately find that there will always be some bound state solution trapped at the edge. But you get one pair of state for each momentum, and each momentum along the x direction, and as you change kx, you find that this energy will generally change, and that's what gave rise to the dispersion of the edge. So it's exactly the picture that we wanted for the quantum spin Hall effect, and it's physically achieved through the band inversion transition caused by spin orbit coupling. So we got very, very excited. Our science paper got published within a month. And then we searched around for partners to work with to make this mercury parallel quantum well. It turns out there's a distinguished group in Würzburg, Germany, who in the past have spent 20 years working on this material. And they perfected the art. The mobility reached 1 million, close to gallium arsenide, and they can also change the gate. So the important tuning parameter is the thickness and the gate voltage. And what do we expect? We expect if the thickness is thin, then it's a trivial insulator. And then as you change the gate voltage, you will get to a trivial insulator which has very, very high resistance. But if you just grow the layer a little bit thicker, beyond 6 nanometers, which is precisely predicted, a dramatically new effect will happen. That even though you have the conduction band and the valence band, there will be one pair of edge state inside of the gap, which traverses the conduction and the valence band. And in real space is exactly this picture. So now if you try to measure the conductance in the nominally insulating regime, you will still count 2E²/h, because there's one access channel upstairs and another access channel downstairs. And that's exactly what the experimentalist measured. And furthermore, if you vary the width of the conduction channel, according to Ohm's law, you should get higher conductance. But not here, because the conductance only comes from edge state. And no matter how wide you make it, there are still 2 edge states. So it's always 2 independent of the width. And that's kind of the smoking gun that this is edge state conduction. And now they're having a lot of fun with it and really prove that this is due to quantized edge state conduction, as a recent highlight article by Marcus Bürtiger proclaimed, that you can make, for example, English letter H. You pass a current from 1 to 4, but the current cannot go past here. It has to go all the way from 2 to 3 and then to 4. And then you can measure a non-local voltage signal, even though if the current is passed from 1 to 3. The edge state theory is very precise. It tells you all the values of the quantized conductance, and it checks very precisely. So this kind of is established beyond any doubt that this is due to edge state quantized edge state conduction. Yeah, question? Yeah.
Is the odd parity of the P states important for forming?
Yeah, because it gives you the Dirac structure. Because you have the S level and the P level, and the off-diagonal matrix element has to be linear.
So it wouldn't work with D orbital?
The D orbital will not have worked. It depends. If you can have anti-bonding or bonding D orbital, there may be a possibility. But still, there have to be opposite parity so that the K quantum number is linear. That's what the Dirac structure is in these maps. Unfortunately, there was, so this is one system where it worked, but in the case of graphene, it turns out that spin orbit coupling is 10 to the minus 3 millielectron volt. And so in the case of graphene, there's no, we don't expect any quantum spin. But there are other materials, in particular, there's something called indium arsenide gallium antimony. The Cambridge group was the world leading that, and I hope that someday that effort can rebut. But now we can say that how do you generalize this picture from 2 dimension to 3 dimension? So there's a class of material called bismuth selenide. and it has somewhat similar to graphene. It has a layered structure, and the layered structure is stacked quintuple layers. So it also has a center of inversion, so that you can have this situation. So now, if you try to understand the electronic structure of this material, you can proceed it by different stages. First, if you have a quintuple layer, the most obvious thing to do is there's a center of inversion. You form bonding and anti-bonding states. Next stage, you look at crystal field splitting because it's a layered structure. It turns out states closest to the Fermi level are the PZ states, PZ orbitals. But just like Pierce's question pointed out, it's the PZ bonding and the PZ anti-bonding state which are closest to the Fermi level. Now, if you turn on a spin-orbit coupling, there will be also a level inversion that happens. So this system is kind of like the three-dimensional version of Mercury terabyte. So now we write down a kind of a tight binding or continuum model for it. It's also a 4x4 matrix model in this space of the bonding and anti-bonding PZ orbitals. And here, if you, for example, the way to see it's a simple generalization of the Mercury telluride model is if you let the KZ term go to 0, it's exactly the Mercury telluride model that we wrote down. And then it will have, when you solve this model, because of the level inversion, it will have a single Dirac cone on the surface of the three-dimensional material. But it only has one single Dirac cone, so it's only 1/4 of graphene. So this picture is actually taken from the experimental by the Princeton group, that the Dirac cone is a single one at the gamma point, and also like what Ali pointed out, there's a spin chirality, so the spin goes around to the Fermi surface, but there's no degeneracy, there's only one spin state, and the spin is uniquely determined by the momentum. So the IOP group, Daishi, Fangzong, and the Stanford group, we collaborated. It turns out there's a family of 4 materials, and 3 of them come out to be topological, and 1 of them is not. And here's the experiment by the Princeton group, by Harper's, by Sahit Hassan's group, which I already commented. Also beautiful experiment done at Stanford University, photo emission looking at this topological surface state. And here you see this single beautiful Dirac cone localized near the gamma point. So these days, all the leaders who used to work on high-tissue superconductivity are also very involved in the work on topological insulators, but there's an important difference. So when you hear a talk on high-TC, they will tell you that, oh, I work very, very hard, but it's very hard to get rid of the schmutz effect on the surface state. But when you go to the talk in topological insulators, they will tell you, oh, I work very, very hard, but it's pretty hard to get rid of the schmutz effect on the bulk state. And this is actually part of the frustration, that if as grown, these materials, you see this beautiful surface state, but as grown, they also have some bulk state. The Fermi level intersects the bulk state, but you need to do some compensation doping in order to achieve that. But it's actually very exciting news for the experimentalists, because a lot of the technique they have developed are for surface-sensitive probes, and it's ideally suited for this type of experiment. Also, it's exciting news for nanoscience. My colleague Trey Yi's group at Stanford has grown bismuth selenide now in nano-ribbon form, and they also have seen that the conduction mostly coming from these surfaces. The beautiful experiment done by Ali Yasani and also in related material by Kapitunik and by Tsinghua University, Qifeng Chui, really have, through the STM experiment on polyparticle interference, checked that this rule of no backscattering, which I explained through the fact that if you rotate a spin by 2 pi, it will give you a minus sign, this destructive interference, guaranteed destructive interference, cannot be experimentally seen by SDN experiments. So now let me come back to your question. What exactly is the definition of a topological insulator? What's topological about a topological insulator? It turns out very, very simple. You can understand the definition at the Jackson level, okay, ENN. So if you have an insulator, if I integrate, it can be a strongly interacting insulator. If I integrate all the electronic degree of freedom, I will end up with a Maxwell action, which is E squared minus B squared. And the coefficient of E squared tell me about the dialectical constant of the material, and the coefficient before B squared tell me about the magnetic permeability. And in terms of electrodynamics of the insulator, that's what we're taught. At long distance, these are the only two important parameters. But when we read Jackson even more carefully, some of us may say, what about another possible term? Here's E squared and here's B squared. What about E dot B? It turns out this term is a topological term. I will explain a little bit more why it is a topological term. Okay? But naively, you say that this term shouldn't be allowed because E is even under time reversal, but B is odd in the time reversal. So naively, you will say this term, if I have a permeating insulator, it shall not be allowed. But it turns out that precisely because this is a topological term, there is two choices of the coefficient. Either when it's 0 or when it's pi, it still preserves time reversal symmetry. And that's because there's a periodicity in theta. When you change theta by 2 pi, it does not change. But pi and minus pi are the same modulo 2 pi. So it's for this reason that all insulators which are paramagnetic, non-magnetic insulators, in principle should be described by three numbers, epsilon, mu, and the theta. And theta can only take two possible values, either 0 or pi. And when it's pi, it's called the topologically non-trivial insulator. We'll discuss the physical meaning of this later. But this is kind of the general topological sense. So there were earlier works which defined the topological insulator using momentum space, and it's nice and very beautiful. But this definition is more general because this momentum space picture only works when you have non-interacting particles, and they don't exist in nature. Whereas for any insulators, this general definition is valid.
Question.
Yeah?
Within the bounds of purely classical physics, is it allowed?
No, because it requires the quantization, because the h bar has to come in. So this theta has a coefficient which is exactly the fine structure constant, E squared over h bar c. Within classical physics, there will be no quantization and no periodicity of theta going to theta plus 2 pi. So it has to be a quantum mechanical effect. And as you have seen, the other explanation I gave is the minus sign comes from the spin, so it has to be quantum mechanical. So it's kind of the most striking manifestation of quantum matter. Now, why is this term topological? When you write E dot B in covariant notation, it's F mu times F mu dual. And again, it involves the epsilon tensor, not a metric tensor. And that's why it's independent of the geometry, but only dependent on the topology. Furthermore, E dot B is a total derivative. It's a total derivative of the transition term. And when you write take theta equals to pi, what it means is that because transition term can define a surface quantum Hall effect, and that implies a quantum Hall conductance of 1/2 E squared over h. Now that 1/2 should be quite familiar to some of you who studied graphene. When people discovered quantum Hall effect in graphene, they say that the quantized Hall conductance is 1/2, but times 4 E squared over h, because in graphene there are 4 derived quantities. But on the surface of a topological insulator, we have only one and a single derived form. So this is really 1/2, not in units of 4, but in units of the honest E squared over h. And that's another reason why the topological surface state is stable. Because if you start with 1/2 E squared over h, any disorder can only jump you by integer. So if you have integer, then by some amount of disorder you can get to 0. But if you have 1/2, if you put too much disorder, you get minus 1/2. You can never get 0. And that's another way to understand why 1. So there are some dramatic effects of topological insulators. If you put a charge above some insulator, normally you will get an image charge, as we are taught in high school and by Jackson. But here, because we have a new topological term describing the macroscopic electrodynamics of a topological insulator, you predict that the image is a magnetic monomer. Okay, so this seems like a dramatic statement, but you can again check it experimentally by a magnetic atomic force microscope. You can put a charge above the surface, you see an image charge, you image the magnetic field, and you find that it goes like one of our squirrels, not one of our cubes. The new frontier of this field is to, so far, most of these could be called topological semiconductors or Banning insulators, but the new frontier is to look for topological Mott insulators. One fundamental question we can ask in this field is whether spin-orbit coupling is absolutely essential. It turns out it's absolutely essential if you have non-interacting fermions. But if you have interacting fermions, the interaction can dynamically generate for you a spin-orbit coupling. And that's proposed by us in this PRL. So it turns out when you look for Mott physics interplay with spin-orbit physics, the most promising place in the periodic table is to look at 5D transition metal elements. And Naoto Nagosa and us have a proposal about iridium oxide being a fruitful place to look for such effect. Very recently, Piers Coleman and colleagues have proposed topological conduit insulators, so now it's connecting to heavy fermions, and that is really kind of an exciting proposal, marrying strong correlation physics with spin-orbit physics. Now, we can also, another frontier is to generalize from topological insulator to topological superconductors. The basic picture is characterized by these 4 cartoon pictures in our recent PRL paper. In the quantum Hall effect, as I reminded you, the fundamental equation is 2 equals to 1 plus 1. So 2 channels are broken into 1 channel and another 1. So now how can you break 1 even further? It turns out 1 can be again broken into 1 half plus 1 half. And that's when you go to a superconductor. Because these chiral edge have both a particle version and a hole version. But when you go to something called a chiral superconductor, it turns out that you only have particles but no holes. And that's called chiral Majorana fermions. Similarly, if you have quantum spin Hall effect, 4 equals to 2 plus 2, you have 2 edge states on the edge. But if you go to the superconducting version of it, it's almost like the same Hamiltonian, but with the distinction that inside the superconductor you have a gap, just like the insulator has a gap, but the edge state only has 1 half, only has the particle branch, but no hole branch. And these are called Majorana fermions. And these are very, very interesting, exciting objects, even relevant for topological quantum computing. What is the physical realization of such a topological superconductor? We don't know yet. But we do know for sure that the topological supergroup, which is the helium-3b phase, is a realization. So you remember the topological insulator has a Dirac cone, but on the surface of helium-3b in the bulk is fully gapped. But on the surface, we predict it's not a Dirac cone, but a Majorana cone. That it has a particle cone, but no hole cone. Everything else is identically the same as topological insulators. And we very recently proposed the experiment to shoot an electron into the helium-3, digging itself a bubble, and by the ESR signal, comparing the bulk versus the surface, you can detect such a Majorana. So let me come to the conclusion of this talk. So we're really at a very exciting stage in condensed matter physics. There's basically a new dimension in the topological phase of matter. So that very much reminds me of Einstein's dream. He said that the most fundamental laws of physics are geometrical laws, and they're beautiful and they're fundamental. But when you really pursue this dream even one step further, and indeed the fundamental laws in particle physics are expressed in terms of geometrical principles of curvature of space and curvature in the gauge fields. So if you pursue this dream even one step further, you will say, why stop at geometry? Why shouldn't the most fundamental laws of nature to be topological laws and topological field equations? That's an illustration of topology of a cup going to a donut. But when you look at the standard model, it indeed has mostly description in terms of these geometrical laws of physics, but there's only one term which hints at the topological structure of the standard model. And that's exactly the identical term that we have proposed as the description of the topological insulator. It's exactly an E dot B kind of term. And that's why recently Frank Wilczek got very interested and very excited. And he says that indeed, by studying topological insulators, it's even give us a window into the laws of nature and into the universe. So this theta angle is one of the most important kind of physics measurement trying to determine that, but we have already determined that in quantum metaphysics. And you can even promote that into a field, in which case it will be called an axion field. And it's again one of the most sought after particle in field theory, and it could even be a candidate for dark matter of the universe. So here at the ICAM conference, I see very nice category of quantum matter, soft matter, living matter. I hope that someday we'll also see dark matter. So for those of you who would like to follow up, this January issue of Physics Today, we invited to write a feature article, and this is the beautiful Gerard poem on the surface of topological insulators, and there's also a YouTube video, which MIT did a very nice recording of my colloquium lecture, and it's uploaded to the YouTube. Thank you very much. Yeah, screen.
Yes, you mentioned that the states are topologically protected.
Yeah.
Of course, this concept has been discussed a lot in another area, particularly by Kitaya, namely in quantum computation.
Yeah.
Do you somehow foresee that these states might be useful in that way?
Yeah. So that's indeed what we're saying. There's you can, if you go to topological superconductor, you can have the vortex state of the topological superconductor containing -1 fermions or -1 zero modes, and these are kind of this system may be the most reasonable, physically reasonable realization of the proposal. Charlie King and Fu had a very nice proposal to put a superconductor in proximity with topological insulator surface state, and they will again have So this very idea of topological robustness is indeed very essential for robust quantum information processing.
I listened to a talk last summer by Imada, in which he was discussing Mott insulators.
Yes.
And of course, it's always possible I misunderstand the theory talk, but if I understood him rightly, he said that if one had a Mott insulator, by which I took him to mean one where it didn't have some symmetry breaking, magnetism,
Right.
this or that, that it had to be a topological insulator. It is a very strong statement.
Yeah.
And I wondered whether that would connect. Well, I don't know. How you react? Did I misunderstand him, or could that be?
Yeah, maybe it's true in some sense, but I think I don't know how well defined that statement is. But in this subject, at least everything we say is very well defined and backed up by sharp equations. So maybe he meant such a model insulator will have to have theta equals to 1. There's only two possibilities. Either theta equals to 0 or theta equals to 1. Yeah.
You mentioned Wilson's comment that we might. So if you go to a system like a work system and things like that,
Yeah.
another flavor, flavors.
Yeah.
So you have isospin and
Yeah.
things like that.
Yeah.
So how do you generalize?
Yeah, this is a very, very good question. The very first reaction, people in the quantum matter community, they will say, what about not spin, but to say two orbitals,
Right.
or pseudo spin as you have in graphene. It turns out they were not for a very, very good reason. Because I argue the most important thing, if you call something spin, the important test is to rotate that spin by 2 pi. If you give it -1, it will work. If you give it +1, it will not work. But any orbital degeneracy, when you rotate by 2 pi, will give you +1 so it will not work. In a very sharply defined sense.
So
Ali.
you showed the spectrum of the topological superconductor.
Yeah.
And half of the spectrum missing.
Yeah.
Is that what you meant?
Yeah, and I can be a lot more precise. Okay, if you take the BCS mean field Hamiltonian for helium-3, it looks term by term identical. to the model we proposed for example, a three-dimensional topological insulator business terabytes. So now you can how can that be? One is an insulator, one is
P-wave superconductor.
yeah, one is a P-wave superconductor, the other is an insulator. How can they have identically the same Hamiltonian? It turns out that when you look at the Hamiltonian for the insulator, it's in the basis of Pz plus Pz minus spin up, spin down. So you have two orbitals spin up, spin down. But helium has only one orbital, but spin up, spin down. So in order to write down such a 4x4 model, you are taking the Nambu notation. You take sine and sine diagonal, and then you prove. So in writing down such a Hamiltonian, even though it looks identically the same, you artificially double the degree of freedom through the Nambu notation. So therefore, after you solve all the equations, you get a beautiful Dirac form. You have to pay the price back. You have to chop away half of it. And that's how you go from Dirac to Majorana.
So you find the chemical potential and
Yeah,
below
in the case of superconductor, the chemical potential always has to sit at the top.
yeah.
And then the other lower one, because you artificially double, you have to chop it away.
It's just nothing there.
No, but that's a theoretical way of doing it. It's called imposing a reality condition. It's remarkable. These two Hamiltonian are identical. But the very fact that we know business terabyte has a single Dirac form, we would know that helium speed will have a single one.
Okay, I'm going to thank Shoucheng for his great talk.